All right, today we're jumping into a topic that can sometimes feel like a real beast in algebra, dividing polynomials. But trust me, we're going to tame it. We're not just going to show you how to do it, we're going to show you why. It's one of the most powerful tools you can have in your math toolkit.
Okay, before we get lost in all the x's and exponents, let's take a step back to something we all get. Simple division. Like 9 divided by 2. It goes in 4 times, right? And you've got 1 left over. That's your quotient and your remainder. Hang on to that idea because that exact same logic is going to be our guide for everything we do next.
So what happens when we swap out those nice, simple numbers for something that looks, well, like this? How in the world do you even start with a problem like this? It looks messy, I know, but stick with me because by the end of this, you're not only going to have 2 ways to solve it, you're going to understand a really cool secret that's hidden inside.
So you might be asking, why do I even need to do this? And that's a fair question. Think of it like this. Dividing polynomials is like being a detective for equations. It lets us break down these big, complicated expressions into their simpler parts or factors. It's absolutely essential for finding the roots of an equation and really understanding what it's doing.
All right, quick refresher, just so we're all on the same page. What even is a polynomial? Well, it's just a fancy name for an expression with a bunch of terms added or subtracted. You've got variables, you've got numbers, and you've got exponents. But, and this is key, the exponents have to be nice, whole numbers, no fractions, no negatives. That's it. So, method number 1. This is the old classic, the trusty workhorse, long division. This is your all-purpose tool. It might not always be the fastest, but it will always work no matter what you're dividing. And you know what? It's going to look surprisingly familiar, just like the long division you did way back in grade school. The entire process, and I mean the entire thing, just boils down to a simple 4-step dance that you just repeat over and over again. You divide, you multiply, you subtract, and you bring down the next term. Then you do it all again. That's the loop. Let's see it in action. Okay, let's walk through this example. First step, and this is key, you ignore everything else. Just look at the very first term of what you're dividing, the x squared, and the very first term of what you're dividing by, the x. So what's x squared divided by x? It's just x, and that x goes right on top. Simple as that. Now, we take that x that we just put on top, and we multiply it by the entire divisor, the whole x plus 1. So x times x is x squared, and x times 1 is 1x. We write that result right underneath, making sure we line up the terms. Easy. All right, pay close attention here because this is the number 1 spot where people trip up. We have to subtract that entire line. Now, the easiest way to avoid mistakes is to think of it as adding the opposite. So just go through and flip the sign of every term on the bottom. The positive x squared becomes negative, the positive 1x becomes negative. Now you just add. The x squareds cancel out, and negative 9x plus negative 1x gives us negative 10x. Then we just bring down the next term, run through that loop one more time, and boom, we're done. How do we know we're done? Because our remainder, which is a big fat 0 in this case, has a lower degree than our divisor. And the answer, our quotient, is sitting right there on top, x minus 10. Perfect. Okay, so long division is great. It's reliable. But what if I told you there's a shortcut, a sleek, faster, more efficient way to get the job done for certain types of problems? It's called synthetic division, and honestly, it's a total game changer. And a little bit of trivia for you. This isn't some newfangled trick. This incredibly clever method was actually developed way back in the early 1800s by an Italian mathematician named Paolo Ruffini, so it's got some history. Now, here's the catch, and it is a big one. You can't use this shortcut all the time. Synthetic division only works if your divisor is super simple. It has to be a linear binomial, meaning the highest power of x is just 1, and it has to be in the form of x minus some number. If you're dividing by an x squared or anything more complicated, you have to go back to long division. So here's where the magic happens. With synthetic division, we get to ditch all the variables and just play with the numbers, the coefficients. You write down the coefficients from the polynomial you're dividing, and for the divisor, you take the root. So if you're dividing by x minus r, you just put r in a little box on the left. And the process itself is almost ridiculously simple. You start by just bringing down that very first number. Then you start a rhythm. Multiply by the number in the box, write the answer in the next column, and add down. Then you do it again. Multiply the new number by the one in the box, write it down, add. You just keep that multiply, add rhythm going until you run out of numbers. Okay, so we've got two solid methods now. The obvious question is, which one should you use and when? Let's put them head to head in a little showdown to make it super clear.
This chart really says it all. Think of it like this. If your divisor is a simple x minus something, then synthetic division is your sports car. It's fast, it's efficient, it's the way to go. But for any other kind of divisor, anything more complex, you have to pull out the reliable old truck, long division. It might be a little slower, but it can handle any road.
So we've learned how to find the answer. But what if I told you the most important part of this whole process isn't really the answer at all? It's that little number you get at the very end, the remainder. It turns out it's not just the leftover. It's actually a secret message.
It all comes from this official-sounding rule called the division algorithm. Now, don't let the name scare you. All this says is that the polynomial you started with, p of x, is equal to the thing you divided by, x minus r, times your answer, q of x, plus whatever was left over, the remainder r. That's it. Now watch this, because this is the really cool part. What happens if we take that number r from our divisor and plug it into the equation for x? Well, that first part, the r minus r, just becomes 0. And what happens when you multiply by 0? The whole term just, poof, it vanishes. And look at what you're left with. P of r equals r. This is huge. It means the value of the polynomial at r is exactly the same as the remainder you get when you divide by x minus r.
Don't take my word for it. Let's prove it with our earlier problems. Remember that very first example? Dividing by x minus 4 gave us a remainder of 310. Well, this theorem says that if you just plug 4 into that original polynomial, you should get 310. And if you run the numbers, you do. It works every single time. The remainder is a massive shortcut for evaluating a function.
I mean, just think about this last example. To find p of 6 the old-fashioned way, you'd have to calculate 6 to the 4th power and 6 cubed. You'd be punching numbers into a calculator for a while. But with a few quick steps of synthetic division, bam, the answer is just sitting there. The remainder was 4,825, which means p of 6 is 4,825. That is the incredible power of this secret.
So, you see, polynomial division isn't just about finding an answer. It's a tool for uncovering deeper connections and hidden values inside an equation. And it really makes you wonder, doesn't it? What other amazing secrets and shortcuts are hiding in plain sight in the math you thought you already knew? Thanks for joining me.